Hello students, yes, okay. Yeah, so I hope I'm audible to you all and the screen is clearly visible. So welcome to this session of this 6th lecture or the 7th lecture of this external fluid flows in this fluid mechanics Abhyas course. Okay, so in this course, in this module, we'll see this external viscous flows. We will talk about the boundary layer theories on the flat plates on the bodies actually, and also we'll talk about the concepts of drag quickly, and then we'll go to the problems that we discuss in this lecture basically. Okay, yeah, good morning. So first let us right away start with the first problem of this class today. So consider the following velocity profile. U by u naught is equal to y by delta whole to the power 1 by 7. At a particular section of a flat plate, the boundary layer thickness is 3 centimeters and the free stream velocity is 12 meters per second. If the discharge to the boundary layer region is 5 meter cube per second per meter width, then the energy loss in terms of airhead is dash meters, of course. Okay, round off up to 3 decimal places, and density of air is taken as 1.2 kg per meter cube. Yes, good morning all of you. So let us try to attempt this question quickly. So there is a boundary layer profile. So if you see, there is a plate actually. There is a plate, and of course on this plate there is some boundary layer which got developed at this section. Okay, so if you see at this section, particularly at this section, we have some boundary layer thickness. So let us suppose there is some velocity profile that existed here. Okay, and this is given as u by this free stream velocity at the inlet. At the inlet we have the free stream velocity capital U. So if this is the free stream velocity, then these two are related by y by delta whole to the power 1 by 7. Okay, so if this is y by delta whole to the power 1 by 7, then at a particular section of the flat plate, the boundary layer thickness is 3 centimeters. Okay, so here it's given, if you call this value as boundary layer thickness, which is your delta, standardly we have this value of delta as 3 centimeters here, correct? So they have given you this delta is boundary layer thickness is 3 centimeters. So if this boundary layer thickness is 3 centimeters and the free stream velocity is 12 meters per second, okay, so we have this free stream velocity which is 12 meters per second in this case. Okay, so this is 12 meters per second. If the discharge to the boundary layer is 5 meter cube per second per meter width, so when width of the plate is 1, the discharge to this boundary layer region is how much? 5 meter cube per second actually. Okay, so this is the discharge. Now per meter width, the energy loss in terms of airhead is dash. So first of all, look, try to understand one thing. What is energy loss? Kinetic energy loss basically. Okay, now if this plate is not here, for example, let us suppose if this plate is fixed. Now if this plate is not here, then the mass which is entering this plate would have moved at capital U velocity. But because of the presence of this plate, what's happening here? The velocity profile got, it took a particular velocity profile that small u by capital U is equal to y by delta whole to the power 1 by 7. Okay, so if this is the velocity profile, they are asking you what is the loss in the energy. Clear? So now let us see. If you see, out of displacement thickness, momentum thickness and energy thickness, please tell me what thickness is actually compensating for the energy loss, because actually if you see here, the fluid particles do not travel at capital U velocity, correct? Along this section, the fluid particles do not travel at capital U velocity. So for this, what we do is we develop some excess section which is called the energy thickness, correct? So this energy of the fluid flowing in this thickness of energy thickness is actually compensating the loss in the kinetic energy of the fluid in this section, correct? Yes, it is basically energy thickness. So energy thickness actually compensates for the loss in the kinetic energy thickness. So let us calculate what is the delta star basically. Okay, kinetic energy loss, if you write, kinetic energy loss is equal to whatever is the loss that is happening here, that is nothing but the kinetic energy of the fluid passing through this delta star. So if you take this delta star value, for example, if you take this delta double star value, which is energy thickness, so this value is equal to, what is the amount of fluid that is flowing here? This is flowing at capital U velocity, because once the boundary layer is crossed, again every layer flows at capital U velocity. So half times mass can be written as density into volume. So density into, now what is the volume of the fluid actually, because half into mass flow rate we can write kinetic energy rate loss, if you write half into rho into U into W, correct? Half into rho into W into double star. So this is the total mass flow rate that is passing through this small section, because rho into AV is equal to basically this value. So half mass flow rate into this capital U square, correct? Because this is the velocity square. So total kinetic energy is equal to half mass flow rate into U square. Mass flow rate is nothing but density times this U into mass W into delta double star is the area available for the flow, and at this area every particle is moving with capital U velocity. So this is the total expression for this kinetic energy loss, correct? So this is equal to half times of rho into W is 1 anyhow, so U cube into delta double star, which is the energy thickness value. So let us see what is the expression for energy thickness value. We know delta double star is equal to delta double star, which is your energy thickness, is equal to integral 0 to delta U by capital U times of 1 minus U by capital U whole square dy. Correct? This is what we have. Correct? This is the expression for the energy thickness. Basically, we have derived this in many fluid mechanics courses. You might have seen this expression. The energy thickness of any velocity profile is given by small u by capital U times of 1 minus small u by capital U whole square into dy. So, is this clear to all of you? Did you all understand how I have written the rate of kinetic energy loss here? So please type in the chat box. Did you all understand how I have written the kinetic energy loss here? Because rate of kinetic energy loss is nothing but half times mass flow rate into U square. Basically, so this mass flow rate is written as density times area into this velocity. So rho AV. Clear? Abhimanyu, Pritham. So please type in the chat box. Is this clear to you? Did you all understand how the kinetic energy rate loss is actually equal to this quantity, which is half times rho U cube into delta double star? Yes? Okay, so now let us substitute this velocity profile. Given, what is the velocity profile that is given? Given U by capital U at this location is how much? Y by delta whole power 1 by 7. Okay, so Y by delta whole to the power 1 by 7. So let us substitute here. So if you substitute and if you integrate, this gives you delta double star is equal to integral 0 to delta Y by 7 whole power 1 by 7 minus, this is U by capital U whole cube, which means Y by, this is delta actually. So Y by delta whole power 1 by 7, and here it is Y by delta whole power 3 by 7 dy. So upon integration, what this values gives you? Integration of Y by delta whole power 1 by 7 is, okay, so see here, Y by delta whole to the power 1 by 7 is basically, if you integrate this delta power 1 by 7 is constant. Delta power 1 by 7, because at a given section delta has some finite value. So delta power 1 by 7 into integration of y power 1 by 7 is actually y power 1 by 7 plus 1 divided by 1 by 7 plus 1. Correct? So totally it is 7 by 8 times of y to the power 8 by 7 minus, coming to here, 1 by delta power 3 by 7 times of y power 3 by 7 plus 1 divided by 3 by 7 plus 1. So total 7 by 10 times of y power 10 by 7. Correct? This is what we have actually. So this value within the limits 0 to delta. Just I'm calculating some integration. That's it. Okay. Mathematically, we are just calculating some integration. So this is equal to, now if you replace this value of delta, then you have some expression. If you replace 0, everywhere it is 0 actually. Clear? So that's why if you see, this y is not here, right? This y is not here, right? 1 by delta power 3 by 7 into integration of y power 3 by 7 is this. Now 7 by 8 times of delta power 8 by 7 by delta power 1 by 7. So total delta minus 7 by 10 times of this also gives you a delta here. So if you simplify this, 7 if you take out, then 10 minus 8, 2 divided by 80 times of delta. So this gives you 7 by, means basically if you simplify this 40 times, so 7 by 40 times of delta is the actual energy thickness. Correct? So 7 by 40 times of delta. Correct? Yes, so 7 by 40 times of delta, if you see, this is the value of delta star. So delta double star energy thickness is equal to 7 by 40 times of delta. Okay, so this is energy thickness. So if this is 7 by 40 times of delta, then if you replace here, we will get the total kinetic energy loss. Now what they are asking you? They are asking you, then the energy loss in terms of airhead is dash. So they want this energy loss in terms of airhead. So means this energy loss rate is equal to mass flow rate of air into this head loss. Okay. So what is the expression for this head loss then? Total energy rate loss divided by, this can be written as density into discharge, because I think discharge is given 5 meter cube per second. So this is the expression. So energy loss we have identified just now. This is 7 by 40 times. If you multiply here, then E dot loss is equal to, how much is this? Half rho capital U cube into this 7 by 40 times of delta. 7 by 40 times of this delta. Okay, so this value is actually equal to this E dot loss. So HL value should be calculated. Okay, so how shall we calculate? So please type in the chat box. We can do this simply. Let me take a empty slide again. Okay, fine. So if you see HL, HL is equal to E dot loss. What is E dot loss? Half. Okay, if you simplify this, 7 by 80 times 7 by 80 times rho u cube delta divided with this. What about this fluid? Air, density of air into discharge. So density of air into discharge. So what is the discharge value here? So please tell me what is the discharge value? 5 meter cube per second. Okay, so 5 meter cube per second. So Q. So if you can simplify these values, rho and this gets cancelled. So 7 by 80 times of 7 by 80 times of, okay, so yeah, 7 by 80 times of, let us see, 7 by 80 times u cube. What is free stream velocity? Free stream velocity we have noted here 12 meters per second, correct? So this is 12 meters per second. 12 cube into delta. So what is the boundary layer thickness at this location? 3 centimeters. So 3 into 10 to the power minus 2 divided by Q. Q is actually 5 meter cube per second. So if you simplify, your answer is going to be in meters. Okay, head loss we are going to measure in terms of this air head. So if you simplify this value, I think you will get the answer. So let us simplify. Let us take a calculator and let us, work out this. So how we can do this? 7 into, okay, nothing to simplify, we directly will do 7 into 12 cube. Okay, so 7 into 12 cube into 3 into 10 to the power minus 2. So into 10 to the power minus 2 means 0.01, 362.88 divided by 400 actually. Okay, so divided by 400, 0.9072. 0.9072 meters is the head loss in terms of air head. Clear? So this is how we get 0.9072 meters for this total kinetic energy loss head in terms of air actually. Okay, here we have written this expression for the KE loss. Then in this expression the only unknown quantity here is this delta double star. So if you evaluate this expression for delta double star using our simple calculations, then we got this delta double star as 7 by 40 times of delta for this particular velocity profile. Okay, now once you get this, you can substitute there and we have equated both the terms, that HL value is equal to 7 by 80 times these guys. So density got cancelled. So we have the rest of the expression. So we substituted. Okay. Okay, fine. So let us see here. So that's why if you see 0.90 something came. So 0. How much is this? 9072. So 0.907. How many decimal places? Up to 3 decimal places. So 0.907 you can take, which is 0.855 to 0.946. So this value is within this range. Okay, so that's how we have 0.907 meters. Okay, so yesterday class one question which is related to manometer calculation. Okay, it is correct. So I think we have done some errors in previous question, so some calculations. So as I told you, key got jumbled in yesterday's class. Okay, so it happened. Okay, Abhimanyu, so let's I took care today that no key got mismatched actually. Okay, fine, let us continue. So is this question clear to all of you? They have asked what is the kinetic energy loss in terms of this air head. Okay, so did you all understand how we have calculated this? Every one of you, is this clear to all of you? Okay, now basically I know when we are doing topic wise questions, it's not quite possible for you to discuss all the models. So we are taking slightly complicated models here in the class and we are discussing. Okay, but when we have the complete session for fluid mechanics, means basically on 16th we have the complete fluid mechanics revision kind of course, revision kind of lecture, then I'll keep more questions on linear momentum, angular momentum, Bernoulli's equation and many other topics actually. Okay, we'll put more questions from the topics which we could not cover during the individual topics. Okay, even though now we are covering 90% of the models, but still something is left, we'll definitely do that in the complete fluid mechanics class, okay, of Abhyas. Clear? So let's go for the next question quickly. So let us try to solve this question. A flat plate 0.3 meters long and 2 meters wide is placed along a 1.2 meters per second flow of water at 15 degrees Celsius. So normal temperature. Assume the boundary layer on each face is laminar, of course, and the velocity profile is given by linear profile. U by capital U is equal to y by delta, for which delta by x is given by this relation. Okay, so normally it's a, so give basic idea of displacement thickness and energy thickness shortly. Yeah, okay, I'll give you. Okay, so okay, fine. After solving this question, I'll spend some time and I'll give you what is the exact meaning of displacement, momentum, and also this energy thicknesses. Clear? Okay, now let us see here, for which delta by x is equal to 3.46 by square root of Rex. If viscosity of water is 1.1 into 10 power minus 6 Pascal second and density is of course 1000 kg per meter cube, then the drag force on the plate is dash. So they have given you a velocity profile and they have also given you the variation of this delta with respect to x. Okay, so they are asking you what is the drag force. So how we calculate the drag force? Let us see. Basically, let us suppose you have a plate. You have a plate, for example, like this. There is fluid that is flowing on both the sides, so obviously there is boundary layer that gets developed on both sides. If I want to calculate total drag force, tell me one thing. If I want to calculate total drag force, if I calculate drag force acting on one face and if I multiply it by 2, then can I get the answer? Yes or no? Because situations are symmetric on both sides of the plate. So that means if I want the total drag force acting on my plate, if I calculate drag force acting on one side and if I multiply it with 2, then can I get the total drag force acting on the plate? Yes, I can get it, right? So if I can get it, first of all, let us calculate on the upper half and let us multiply it by 2. Now what happened, how we actually calculate the drag force is, obviously when the fluid is trying to flow in this direction, the fluid will try to take this plate along with the flow. But this plate is actually held by something. So now what happens, there is some drag force acting on the fluid. Okay, so let us see what is the drag force. Let us suppose if you define a coordinate axis from here in this direction. So let us say this is x. If this is 0, x is equal to 0, and let us say this is x is equal to L. Okay, so this is x is equal to L. Now if this is x is equal to L, how do you actually calculate the drag force? Look, let us suppose if you take a small section here. If you take a small section here out of this plate length L, now let us suppose if this thickness of this section is dx, for example, and at this location the shear stress at the wall is tau w, for example. Okay, and let us suppose the thickness of the plate is b, then within this small location, if I want to calculate what is the force acting by the fluid on the plate, can I write the small force, elemental force acting is actually equal to this shear stress into area, which is b into dx. Can I write this? So please tell me, can I write this expression? dFd means the small drag force acting at this particular section of the plate is equal to shear stress acting at the wall at that location multiplied by the total area available for the fluid solid contact here, so which is b into dx. Can I write this expression? So please type in the chat box, can I write this? Tau w times of b into dx. Can I write this expression very shortly? Okay, now if I can write this, now let us see what happened. How we calculate this tau w? Tau w, if you see, we can calculate this as using Newton's law of viscosity, assuming this as Newtonian fluid, du by dy. But this gradient value at y is equal to 0, okay? Because if you take this as the y direction, for example, if you take this as the y direction, then obviously this, if you take this as the y direction, if you take this as the y direction, then obviously this x-axis is nothing but y is equal to 0. So from Newton's law, we can write tau w is equal to mu times of du by dy at y is equal to 0. So what is the velocity profile that is given? U is equal to, let us see, u is equal to y, capital U y by delta. Capital U y by delta, it's a linear function. So this implies your du by dy is equal to capital U by delta. That's it. Okay, now at y equal to 0 or at any other value, this velocity gradient is a constant value, which is u by delta, correct? But delta value changes with location, so definitely this total du by dy changes with respect to location. But at this location, at any y coordinate, this tau is actually same. Okay, now let us see here, du by dy is equal to u by delta. So what is tau w then? This implies tau w is equal to mu times of dynamic viscosity times of this du by dy, which is capital U by delta. Now if you want drag force, you need to integrate this expression. To integrate this expression, b is a constant value, width of the plate is actually constant. But what is tau w? You need to write tau w in terms of x, and exactly for that they have given you this function, that delta is function of this value. Okay, so what is root rex? Let us see. Root rex, Reynolds number at a section x, means let us suppose if this length is x, for example, let us suppose if this length is x, then what are the properties there? Square root of, okay, so you know Reynolds value is equal to Vd by mu, correct? So if you see rho Vd by mu, so we can write that as u x by this kinematic viscosity, mu x by kinematic viscosity. Okay, so this is how we can write the Reynolds number. Okay, so now what is this expression for this delta? Delta is equal to 3.46 x by root Rex. So delta is equal to 3.46 x by square root of Rex, which is square root of this value, which is u x by nu. So you can cancel one x and we can get a square root of x here. So this is equal to, if you multiply carefully, what you will get. Okay, let us leave like this. So this is the expression for delta, or let us write once, 3.46 times square root of x divided by this value can be multiplied here again, so square root of this kinematic viscosity by u. Okay, so we can write this expression basically. Here one you can keep. So this is the expression for delta. So if you replace this here, this implies your tau w at this location, at any location x basically, is equal to mu times u by delta. So divided by this value gives you square root of u by kinematic viscosity by 3.46 into square root of x. This is the expression for tau x. So if you see in this expression, therefore dfd, the small elemental drag force that is acting, dfd is equal to tau w, which is this mu u power 3 by 2, you can say capital U power 3 by 2 divided by square root of 3.46 into square root of kinematic viscosity. So all these are constants. Okay, into 1 by root x. So this is the total shear stress expression multiplied with b into dx. So this is the total expression for the drag force at that small element dx. Okay, so are you all clear with this expression, how we have achieved this expression? Because we have to write, if you want to evaluate this expression, you need to integrate this. For integration, you need this tau w in terms of x. So tau w in terms of x can be written by this equation if you write delta in terms of x. So please confirm, are you all clear with this expression? Everyone, Raushan, Vishal, Tripathi, Abhimanyu, Preetham, all of you guys. So type in the chat box, is this clear to you? Okay. Now let us, if it's clear, then let us go for the next part. So if you want the total force, then obviously you need to go for the integration. Okay. So therefore total drag force is equal to clear. So total drag force is equal to Fd, which is, now the plate is of length L, for example, x is equal to 0 to x is equal to L, then all these values, mu capital U power 3 by 2 into b, this is also constant, width of the plate, by 3.46 times square root of nu into this 1 by root x dx, 1 by square root of x dx. So this is the value which is with you. Okay, now what is the width of the plate? Let us see here. So density is this much, then the drag force on the plate is dash newtons. What is width? That plate is 2 meters wide. Okay, width of the plate is 2 meters anyhow, and there is some flow rate and all. So let us do this integration. If you do this integration, then things gets cleared. Let us see. Oh, just a minute. Let us integrate that carefully and let us try to get the expression value. Okay, so now if you see this complete terms which are here, all these terms, this combination is a constant, yes or no? Because dynamic viscosity of the fluid is constant, free stream velocity, which is some given value, width of the plate is a constant value, 3.46 is constant, kinematic viscosity of the fluid is also constant. So this complete term what we have written here is actually a constant. So if you do this, this implies Fd on one phase. Of course we are calculating on one phase. This is equal to, what are the expressions here? Mu u power 3 by 2 into, this is b, by 3.46 into, you can write one thing, this kinematic viscosity we can write as square root of mu by rho. Okay, so if you write this, then you will get this, cancel this square root one times and you will get totally square root of density into this mu, correct? So anyhow, let us see that later. So what is this integration? Integration of 1 by root x, which is x power minus 1 by 2. So integration of x power minus 1 by 2 is actually equal to minus 1 by 2 plus 1 by minus 1 by 2 plus 1. So total 2 times of square root of x, correct? So if you see 2 times of square root of x within the limits 0 to L, clear? So this is the integration value. So now let us see some simplifications here. This dynamic viscosity will keep a square root here, and this which is in the denominator goes to the top. So this is equal to square root of rho into mu into u to the power 3 by 2 into b by 3.46 times 2 into square root of x, correct? So this is basically square root of x here. Square root of x is root L, that's it. So length of the plate is known to you. This 2 integration is known to you, because if you see differentiation of root x is 1 by 2 root x. So integration of this value, okay, so we have this 1 by root x, clear? So if you apply this result, then the total value is, let us simplify, square root of, what is density value here? Density is 10 cube. Its fluid is water basically, so this is 10 cube. 10 cube into dynamic viscosity value. So what is dynamic viscosity value? They have given you 1.1 into 10 to the power minus 6. 1.1 into 10 to the power minus 6. So this is the case. Then u power 3 by 2. So what is capital U? Capital U, free stream velocity is given. So free stream velocity along a 1.2 meters per second flow of water. Okay, so if you see, capital U is 1.2. So 1.2 power 3 by 2. What is width of the plate? Width of the plate is 2 meters wide. So this is 2 meters into 1 more 2 from the integration divided by 3.46 into square root of L. L is 0.3, correct? So this is the final expression for calculating the drag force on one edge of the plate. Clear? So please type in the chat box. Is this clear to you? All of you? So type in the chat box. Did you all understand this clear expression? How did we achieve this and how we have written these values? Basically, you know that if you know the shear stress, wall shear stress at some location, then that wall shear stress multiplied by the area available for the fluid solid contact is multiplied. Okay, so tau W into BDX, we have done this analysis. Clear? Okay, so now let us simplify these values slightly. So if you try to simplify this, then this 10 power minus 3 comes out here. So let us see here. Basically, I think there is nothing much to simplify. So this answer is going to be in newtons. Okay, so let us check. Square root of 1.1 into 10 to the power minus 3. So 1.1, first of all, minus 3, 10 power x, this value into 1.1. Okay, so square root of this, we got some value, multiplied with 1.2 whole power 3 by 2. 1.2 whole power 3 by 2, which is 1.5 into 4 by 3.6 into 4 by 3.46. 3.46. Okay, so this is the value multiplied with square root of 0.3, multiplied with 0.3 square root. Okay, so if you simplify, you got 0.0276, correct? 0.0276, 0.0276. But this is only for single phase, correct? Yes or no? This is only for the single phase, only one phase. Now, but both sides of the plate are actually exposed to the fluid flow, correct? It's given assuming the boundary layers on both the sides. If you see, assume the boundary layer on each face is laminar. So basically, the fluid have two phases actually. So if you simplify this result, let us see what turns out. So multiply it with 2, both the phases, 0.055. So total drag force on the plate. Total drag force on plate is equal to 0.055 newtons. 0.055 newtons is what you have. Clear? Yes. So can we solve by skin friction coefficient? Is dynamic viscosity value is so less? Yes, might be, because if you see, normally the dynamic viscosity values of water is 1 centipoise, correct? 1 centipoise. So 10 power minus 2. So if you write, we'll get 10 power minus 3 Newton second per meter square on an average, because dynamic viscosity of water is given like this. Okay, this is centipoise, 1 cp centipoise. That means 10 power minus 3, 10 to the power minus 3 Newton second per meter square, right? Yes or no? Is dynamic viscosity value so less? Yes, they have given this value 1.1 into 10 to the power minus 6 Pascal second, but normally if you take water, you have 10 to the power minus 3 on an average. Clear? Yeah, even by skin friction coefficient, if you evaluate, you will get the same expression, because skin friction coefficient is again some conversion of tau W by rho U infinity square. Okay, half times of course. Okay, so tau W by half rho infinity square gives you this skin friction coefficient. So again, if you calculate, you will come up with the same expression, CFX. Clear? Okay, so let us see what we have. So I hope this expression and evaluation is correct, right? Did you all get the same thing? Did you all get the same thing here? Yes, practically speaking, dynamic viscosity of water is 1 cp, 1 centipoise practically. So if you do this calculation with this 10 power minus 3 here, let us see what happens if you do this calculation with 10 to the power minus 3. So let us see, 10 power minus 3, 10 power minus 3 gets cancelled. Square root of 1.1, 1.1 square root into 1.1 square root into 1.2 whole power 3 by 2, 1.2 whole power 3 by 2, which is 1.5 into 4 by 3.6 into 4 by 3.46 into 0.3 square root into square root of 0.3. So this is the value that you are getting on one side actually. Okay, this is on one side. So on both sides, if you see, you are getting 1.74 something, 1.749. Clear? So this is the same value you all are getting, right? So 0.055 is the correct answer in this case if there is no calculation error. Clear? 1.74 is what we are getting if dynamic viscosity value is 10 power minus 3. I'm talking about. Okay, but in this question they have given you 1.1 into 10 to the power minus 6. So let us use the value which is given in the question. Clear? But practically speaking, the actual values of dynamic viscosity of water lies around 1 centipoise. Okay, 1 cp we call generally in experiments and all, we call it as 1 cp. So 1 centipoise. Clear? Okay. So did you all get this answer? Everyone? Vishal, Roshan, Abhimanyu, all of you guys, did you all get this? If you have get this, then this is the correct answer because we all have solved together, right? Yes. Okay. So yes. So this is the correct answer, 0.055 to this. So let us. Sorry. Okay, so we'll make this to 0.055 newtons. Okay, so 1 decimal place, so 0.055 newtons is what we can write. Okay, so next, let us go for the next question. And before going for the next question, some of you have asked me one thing actually. This displacement boundary, displacement thickness, momentum thickness, and kinetic energy thickness. So give short note. How many of you want this? Do you want me to speak on what is actual displacement thickness, momentum thickness, and also this kinetic energy thickness? Of course, I won't dare the expressions; they are very huge. But physically, I will tell you what are the meanings exactly. Okay, fine. Shall we spend some 2-3 minutes on that? Okay, yeah, definitely. Okay, then I'll talk about it. So see here, we'll take one empty slide first. Okay, so now see. Normally, what happens? Look, I'll explain you some boundary layer concepts actually. Okay, within some 5-10 minutes. So see here. Let us suppose you have a plate, for example. Guys, listen carefully. This is one very important understanding here. Okay, so please listen. So now, if you take this velocity profile, means if you take a section here, just before the inlet, and also just before the exit. Just before the exit. Okay. Now, if you see, let us suppose if you have some flow like this coming at this velocity capital U. Flow velocity capital U. Okay. Now what happens? Whenever different layers of fluid are coming, till this point there is no restriction for the flow. So all the layers are coming at same velocity. But by the time the fluid touches this, means by the time the fluid crosses this section, this plate is nothing like some obstruction to the flow. Okay, which means if you compare this example with an automobile example, for example, okay, so let us see what happens. By the time your vehicle reached here, you applied brakes, then what happened? Obviously the fluids start slowing down. Okay, this fluid, since it's in immediate contact with the plate, it comes to zero velocity. This fluid layer which is here will try to come to a velocity slightly greater than zero velocity. Okay, and similarly here, if you see, this flow continues. Okay, this flow continues like this. But here you have to observe one thing. I'll tell you. See, if you apply mass conservation, for example, let us suppose if you take certain distance delta above this, okay, now what happens? Try to understand here. At this section, if you take the same delta, example, if you take the same delta, this is delta. Now try to understand something. If this is delta, this delta is actually the boundary layer thickness. Means what happens? Here the velocity is 0. Here the velocity is 0 because of no slip condition. Here the velocity will be slightly more as compared to the first point. Slightly velocity keep on increasing, and finally there comes a point where it almost reaches this free stream velocity. Okay, so here the velocity is again almost equal to the free stream velocity. Now, if you see, let us suppose if I draw some streamlines to this flow, for example. Okay, I am drawing the streamlines. If I draw the streamlines to this flow, so let us suppose your first streamline is like this, second streamline is like this. Now, try to tell me one thing. I have to ask you one thing here. Basically in fluid kinematics and all, we have seen the difference between the streamlines or the difference between the stream functions is nothing but the discharge that's happening between these two streamlines, correct? Now, between, if you see, let us suppose some m dot mass is coming here, for example. If some m dot mass is coming here to this both streamlines, okay, in between these two streamlines, some m dot mass is coming. Now tell me, since the fluid is incompressible, you have some water or something, whenever the density is same, if my discharge has to be same here, but you know clearly one thing, here the velocity of all the points, means if you take the velocity of different points here, at all these locations fluid travels with capital U velocity, correct? But here within the two green lines, here at all the points is the fluid traveling with same U velocity? Please tell me. Here at all the locations of y, the fluid is traveling with capital U velocity. So if you take the same thickness here, is the fluid having same velocity here? At all the locations, do the fluid have same velocity capital U? Obviously no, correct? It is less velocity because there is already some effect of the plate, so the layers got slowed down. So whenever the fluid layers got slowed down, but you know one thing, yes, you know one thing, this mass which is entering cannot cross the streamlines, correct? Because there cannot be any flow across the streamlines, means there cannot be any flow which can cut the streamline and go, correct? So the flow which is entering here should lie between the same streamlines here, correct? But velocity got decreased. That means if you have to conserve your mass, rho into a into v, then this density is anyhow constant at both the locations, but this velocity is less at the exit condition. Okay, now whenever the velocity is less at the exit condition, then to maintain the same mass flow rate, what should happen to this area? Please tell me. Your velocity at these locations got reduced. So if you want to maintain the same mass flow rate, because this flow which is entering cannot leave these streamlines, because flow cannot cut the streamlines, it can flow only in between the streamlines. So if the velocity of these points is less, then please tell me what should happen to this streamlines or the flow area? The flow area should increase, correct? Means basically one thing is very clear, if the, yes, streamline should diverge, exactly. Okay, so if you see along the flow streamlines diverge. Okay, along the flow streamlines diverge. Okay, now this diverging goes on, and finally at this location, normally in actual flow condition there could be some streamline passing through this delta location. So because of this flow, because of this velocity getting lowered, this streamline which is here will get deflected by some amount, correct? So this streamline which is actually passing through y is equal to delta will also get deflected by some amount. Yes or no? Can you all understand this concept? So please type in the chat box. Is this concept clear to you? I am telling you, since the streamlines are diverging, obviously at the streamline which is passing through this y is equal to delta will also diverge, means it will also get displaced by some amount. Yes or no? Yes or no? So please type in the chat box. Can you all understand this clearly? Okay, did you all understand this? The streamline which is passing through y is equal to delta should also diverge. So this displacement which is here is called the displacement thickness. Okay, so this delta, this displacement in the streamline which is passing through here is actually a displacement thickness. Clear? And this is actually compensation for the mass that is getting lost because of this velocity profile. Okay, so here what's happening, whatever the mass that is crossing here, same mass is not crossing here, obviously, because the velocity of the flow got reduced. So what we do is, we had this location, we have taken this some deflection of the streamline such that this deflection or this displacement of the streamline is called the displacement thickness, and that displacement thickness for any given velocity profile here, if some velocity profile is given here, u by u infinity is equal to some function of y, for example, okay, then this displacement thickness is actually calculated using integral 0 to delta, delta is that value, u by u infinity, sorry, 1 minus 1 minus u by u infinity times dy. Clear? So this is the expression. I'm not dealing a detailed course, otherwise I would have derived this and shown you how this is coming, but it's very simple. You see, whatever the mass that is getting lost here is the excess mass that is flowing through this displacement thickness of delta star. Okay, if you apply this simple mass conservation, you will get this equation. Okay, so this is how the displacement thickness is talked about. Okay, now coming to momentum thickness and kinetic energy thickness. What is momentum thickness is, look, similarly, now this is the concept of displacement thickness. Now what is momentum thickness is, look, try to understand here. After this point, at every location the flow has u velocity, correct? After this point the flow has capital U velocity at everywhere, because the flow becomes uniform after it crosses the boundary layer. So what we are considering is, because of this slowdown of velocities of particles, there is some loss in the momentum of the fluid, correct? Means if this much mass is coming at capital U, here the mass is going at some different velocity and even the total mass is also not going. So that's why if you see, we consider some excess mass of the fluid such that the momentum of the fluid from this location to this location is actually equal to this location to this location. Okay, so this difference is nothing but the momentum existing here minus the momentum existing here. Okay, so that's how we define this momentum thickness. Momentum thickness is that thickness of the fluid which is considered for compensating the loss in the momentum actually here. Okay, so why there is a loss in momentum? Because the velocity of the layers got slowed down. Okay, so that's why. And if you calculate this thickness of, this is generally denoted with theta, which compensates for the loss of momentum. So theta is equal to integral 0 to delta u by u infinity, if you say, times 1 minus u by u infinity dy. Okay, similarly for the loss in energy, we talk about kinetic energy thickness. That's it. Okay, because the velocities got reduced, so whatever is the loss in the kinetic energy because of the slowing down of the particles, so that is compensated by this energy thickness, which gives you this expression. If you simplify, I'm not doing the balance, but right now I'm just giving you the expressions. U by u infinity times of 1 minus u by u infinity whole square times dy actually here. Okay, I'm not doing a theory course, so that's why we are talking about this. Okay, is drag force loss in momentum? Yes, exactly. That's why if you see the Wankelmann's integral momentum equation, we will get this relation tau at wall divided by rho u infinity square is equal to dou theta by dou x, and this shear stress is actually responsible for the drag force on the plate, and that is compensated with the loss in momentum, because the force which is, we have solved many linear momentum questions and all. Okay, so that's how, if you see, this change of this momentum is actually responsible for this tau w. Okay, of course I'm not deriving this. You need to take a small control volume and you need to balance the forces. It's a simple derivation, not very time taking, but this is the problems course, so I'm just giving you the values. Clear? If you have thought, you would have got the answer. Why tau w and theta are related? Why not delta star or delta double star? Because theta is the momentum thickness for the flow. Clear? That's the reason. Clear? At the rate of change of momentum thickness is given by this value, tau w by rho u infinity square. Okay, Abhimanyu? So did you all understand what is delta, what is displacement thickness, similarly what is this momentum thickness, and what is this energy thickness? Okay, and I would like to tell you one simple point here, one very easy point. Look, try to understand the case. When you apply brakes to this vehicle, means whenever the fluid touches this, try to understand this concept clearly. Let us suppose you take 2 points here. You take 2 points. As soon as, look, tell me, whenever these layers come onto this plate, this layer will start to slow down this layer, yes or no? Then obviously the velocity of this layer comes, it keeps on decreasing, and finally it comes to some static value and it moves at uniform velocity after some time. Okay, after the laminar range got transmitted. Now, if you see, I'll ask you one simple question, you need to answer this. Okay, the layer is coming, you have applied a brake because of the plate, so the layer slightly travels like this. Now tell me, at these 2 locations, if you take the values of velocity as u1 and u2, so please tell me which will be higher out of these 2. The layer is subjected to some braking, so that's why this layer slowly comes to some component or some velocity. So now if you tell me at these 2 locations, if I talk about velocities, at which location the velocity will be higher? 1, correct? Because obviously u1 is higher, and after u1 the fluid layer still slows down, correct? So this will still slow down. Now let us suppose if this thickness is very small, if I calculate du by dy between these 2 points, assuming to be linear, this is very small gap. So at these 2 locations, if I ask you the velocity gradient values du by dy at location 1 and du by dy at location 2. Okay, so let us suppose you have got these values du by dy at location 1 and at location 2. Now if you see carefully, let us suppose if this small deflection in the streamline is neglected, dy is same in both the cases. Now can you tell me, here both the velocities are 0 because the plate is in direct contact with the fluid. So here both the velocities are 0. Now here u1 is greater than u2. Then can you please tell me which difference will be higher? Which difference will be higher here? u1 minus 0 or u2 minus 0? Clearly u1 is greater than u2. So that means u1 minus 0 greater than u2 minus 0. For the same dy, if you see, the velocity gradient at this location is actually higher. Clear? The velocity gradient at this location is actually high. Okay, first case basically. So whenever the velocity gradient is higher here, let us suppose if you assume the fluid as Newtonian fluid, tau is equal to mu into du by dy at y is equal to 0, means very close to the wall. So if you tell me if this du by dy is 0, can you tell me if you talk about shear stress at the wall at this location, shear stress at the wall at this location and also at the second location, first location and second location, can you tell me at which location the shear stress value will be high? Can you tell me at which location the wall shear stress value will be high, first case or second case? First, obviously, correct? It is at the first case. So one thing is very clear from the analysis, as x increases, your shear stress value will decrease. Okay, and also I'd like to ask you one more question at this point. Look, I am explaining all these things without taking any mathematical equations into consideration. Okay, just this du by dy is what I have taken for understanding. Okay, now if you observe one thing, look, if I take a section, 2 sections here, for example, first section and second section, if I take 2 sections, now compared to here the velocity here will be less, compared to here the velocity here will be less, compared to here it is less, compared to here it is less. So by the time it reach free stream velocity, let us suppose this is the value of delta at this section, for example. So let us suppose this is the free stream velocity. Okay, the fluid has reached free stream velocity here. Now by the time this point is at free stream velocity, will this point, means axially on the same x location, means basically on the same value of y, if this point is at free stream velocity, will this point is at free stream velocity? You see, the fluid layers will much slower down as they travel towards the flow. So if this point is at free stream velocity, the same value y point, will it be at free stream velocity in these 2 cases? So please type in the chat box. No, correct? It will be less. Yes. So that's why if you want to find a layer at free stream velocity, you need to go for some more distance, which means one thing is very clear, the boundary layer thickness is limited to this value here, but here it is to some other value. Okay, so that's why if you see, as x increases, your boundary layer thickness will also increase. Clear? Understood? So these 2 are some generally important relations that normally you see later, at later stage after deriving Wonka-Mann's momentum integral equation and all, you will see that delta is directly proportional to x. Here I will show you in the second question. We got some question, right? So in this question, if you see, for example, we have seen this delta is proportional to root x. Okay, so basically as x increases, this delta value increases. Similarly, if you take tau w here, on tau w, this tau w for this x is in the denominator. So as x increases, your tau w will actually decrease. Okay, so this is basically the understanding from this particular analysis. Clear? Got it? How about drag force? You need to take some small integration on this. Okay, you need to take some small elemental like tau w into b dx, then you need to integrate this. Okay, using Wonka-Mann's momentum integral equation, you can get this. See, in this integration, what we'll do is, depending upon the value of this velocity profile, we'll calculate theta. Okay, so then we'll get an expression between this delta and x. Okay, we'll get an expression between delta and x actually. So once you get tau w, we'll calculate the drag force like we have calculated in the previous case. Okay, clear? Oh, I think there is power cut actually since morning, so I think the power backup got finished. It is shouting. Okay, so can you hear me clearly? So can you hear me clearly? This sound is also coming into the mic. Yes, so please type in the chat box. Is this sound is also coming into the mic? Audible? Okay. So if you see, is drag force increases with x? Yes, of course, because if you see drag force, if you see the drag force cannot be taken at any particular location of x. Okay, it should be taken over some lengths actually. Okay, so that's why it depends upon the integration actually. So if you see, means drag force cannot be talked at a particular points like this. Okay, it should be taught at some finite length. Okay, if you talk only at some small elemental area, then what happens? It turns out to be this expression. Okay, on some small elemental expressions, it depends on this tau w. Okay, so if width of the plate is constant, since this tau is decreasing, if you take different elements at that different elements, fd keep on decreasing. Okay, fine. Okay, so let's go for this question quickly. Assuming the velocity distribution in the boundary layer is u by u is equal to 2y minus y by delta whole square, a flat plate having a length of 1.20 meters is placed in a water of velocity 0.2 meters per second and mu water is equal to 10 power minus 3 Newton second per meter square. Then the thickness of the boundary layer at 0.8 meters from the leading edge is dash mm. It's a direct question. So let us see. Assume Blasius solution. You know what is Blasius solution? Basically, if you solve this equation, we'll see the Blasius solution is given by Blasius solution is given by delta is equal to 5 times of x by root Rex. Okay, Reynolds number. And how we calculate Reynolds number at x? U x by kinematic viscosity. Okay, so this can be written as rho u x by mu. This is the value. Clear? Okay, so now if you simplify this result, Rex is equal to ux by nu. Okay, so let us take these values. Rex at x is equal to, what is the location they are asking you? X is equal to what is the location they are asking you here? At that a layer of 0.8 meters from the leading edge. Okay, so x is equal to 0.8. So this is equal to density of the fluid. It is water. So density of the, it is water, right? It is water given. So density, it's not given. So let us take 1000 by default. 1000 times u. The free stream velocity is how much? 0.2 meters per second. 0.2. X is 0.8 by this dynamic viscosity value, which is 10 power minus 3 Newton second per meter square. So if you simplify this, this 10 cube can cancel this values totally 0 to and all. So 16 into 10 power 4. Okay, so this is 16 into 10 power 4, which is less than 2 into 10 power 5. So this is actually in the lambda regime. So we can take this. So this is the Reynolds number value, 16 into 10 power 4. So if you supply here, delta at this location is equal to 5 into 0.8 by square root of this value, which is 16 into 10 to the power 4. Okay, so this value is in meters, but they are asking you the final answer in mm. So let us see, you multiply by a, this is in meters. So you need to multiply this with the 10 cube. Look, if you take this 10 power 4 out of the square root, we'll get a 10 square into 10 cube mm. Okay, so this cancels this 10 times and 10 cancels this 8 times. So this is 40 by square root of 16 times mm. So if you see, this value is 4. So this is 4. So 4 cancel this 10 times. So total 10 mm is the boundary layer thickness here. Okay, it's a simple question. So it's a 10 mm. Okay, they've asked us to calculate this Blasius. Otherwise, we would have done using this velocity profile. Okay, but in gate exams, normally they'll give you this. In gate examinations, they'll give you this approximation that delta is equal to Blasius, of course. Okay, in general, if Blasius is not given, yes, you need to go for the one Kamen's integral equation. From there, you need to evaluate some expression for delta value. Okay, So 10 mm. So in mm there was, so 10 mm, 10.0 to 10.0. Clear? It's just a simple question by taking Blasius approximation, of course. Okay, because without reading this Blasius approximation, if you start doing with the help of this velocity profile, then you'll get some different answer. Okay, so let us try to solve this question. The velocity distribution for water at a radius smaller flowing in a pipe follows the law U is equal to some constant K divided by 4 mu times capital R square minus small r square, where of course capital R is radius of the pipe and mu is the dynamic viscosity of water and K is a constant. Then the expression for the drag force on the pipe for a length L is, so let us check what they're telling you. So we have a pipe actually. So we have a pipe of radius capital R. Okay. So this is a pipe of radius capital R. Okay. So this is a pipe of radius capital R. Okay. Now at a small r distance, for example, if you see what is the velocity profile, we have this velocity profile. U is equal to K by 4 mu times of capital R square minus small r square. Okay, so we have this capital R square minus small r square. So basically if you want to write shear stress at the wall, how you write this? Tau W is equal to mu into du by dy at y is equal to 0 actually, right, normally. But in this expression, if you see, y is always measured from the plate, means from the solid surface. Okay, but here if you see, this is fluid. So if you want to measure y from the solid surface, then let us suppose at a given section, if this dimension is y, so at any location we have this y plus small r is actually equal to capital R, correct? So y from the distance from the solid surface and plus this small r radius is equal to capital R. So small r is equal to capital R minus y. And if you differentiate this, you know, dr is equal to minus dy, because capital R is constant. Okay, so if you want to calculate the velocity gradient at this location, this expression is nothing but tau W is equal to mu into, since dy is minus, so du by dr. But now y is equal to 0 means this point. Now if you want to write this in terms of small r, this small r is equal to capital R, correct? So that's how these two expressions are actually same. So let us see what is the du by dr for this expression. Du by dr is equal to K by 4 mu times of minus 2 times of small r. Now if you want this value at small r is equal to capital R radius, small r is equal to capital R radius 2. So this is minus K times of small r, if you replace with this capital R by 2 times of mu actually. Okay, so du by dr is equal to minus constant times capital R divided by 2 times of this dynamic viscosity value. Okay, now if you replace this value, what they're asking you here, they're asking the total expression for the drag force. So if you take a small element, for example, of thickness dx, if you take a small element like this of thickness dx, for example, okay, dx, this is a pipeline of length L. So let us suppose this is x is equal to 0 and this is x is equal to L. There is a pipeline like this. Okay, now in that case, if you see, if this is the shear stress acting tau W at this location, of course at every location tau W is this value. So what is the drag force because of this shear stress on this small part of the pipe actually? So if you want to see, the small drag force that is acting is equal to minus K capital R by 2 into mu times of, now this shear stress is acting on a surface area which is equal to, if radius of the pipe is capital R, so 2 pi r into dx. This is the area that will be in contact, because 2 pi r is the circumference, dx is the thickness. So internally the fluid touches the pipe for a surface area of 2 pi r into dx. So if you want to calculate the total drag force, okay, this is du by dy value, du by dr. So since if you see, this is du by dr. So if you see, shear stress is actually equal to mu into minus du by dr. So minus of this value gives you K into capital R by 2 mu. So this mu and mu gets cancelled, 2 and 2 also gets cancelled. So pi K R square is constant, pi K capital R is constant here. So pi K capital R square dx. This is the small elemental drag force that is acting on that small section. So if you want for the total pipe, this implies your drag force acting is equal to x is equal to 0 to x is equal to L pi K R square dx. So if you take this pi K R square out as a common term, then integration of dx from 0 to L is actually capital L. So the total drag force that is acting Fd is equal to pi K R square times L. Clear? This is the total drag force that is acting on the plate, of course. Okay, so very simple question. So if you see, we just need to calculate the velocity gradient and just need to integrate it. That's it. Okay, so pi k r square L. So pi k, okay, this is r L square, but this is pi k r square L. So option C is the correct answer for this question in this case. Okay, so let us go for the next question. So let us go for this question. So let us see. For the velocity profile for laminar boundary layer, so it's a laminar boundary layer and the velocity profile is given by this function, some function of y, and assume shear stress tau naught is equal to, means basically the wall shear stress tau naught is equal to this particular expression 0.323 mu u capital U divided by x into root Rex. The drag force varies between limits 0 to L. Of course, if the length of the plate is 0 to L, it varies. The coefficient drag CD is equal to k by root Rel. The value of k is dash actually. Okay, so let us see how you calculate this CD. CD is actually equal to some constant divided by root Rel. Correct? So now if you see this expression, this is CD and this is the expression for tau naught. Okay, so let us write the velocity profile first of all. U by U, capital U actually, is equal to, U by capital U is equal to 3 by 2 times of y by delta minus half times of y by delta whole cube minus half times of y by delta whole cube. Okay, and tau naught. So what is the expression for tau naught? The wall shear stress tau naught, the wall shear stress is equal to 0.323 times of mu u, mu capital U by x into root Rex actually. Okay, so this is square root of Rex. Now they are asking you what is this constant value k. So first of all, how you actually calculate the this CD value? Actually, first of all, if you know the total drag force, for example, if you know this total drag force, then you know this FD is nothing but half times of CD into rho a u square basically. Correct? So this is the expression for the total drag force. So from this expression, if you see, the coefficient of drag is equal to 2 times of FD by rho a u square. Now this CD is also given as k divided by root Rel. So if you equate both these expressions, then definitely you will get the answer. Okay, so how we can actually calculate this? Okay, area, length of the plate is given actually. So length of the plate is 0 to L is given. That's it. Okay, so length of the plate is 0 to L. So anyhow, we'll end up with some expressions in FD in terms of L. Okay, so let us start simplifying. So let us calculate FD. FD is actually equal to 0 tau naught, basically tau naught. If you take small length of the plate for thickness B into dx. Okay, so this is the shear stress and this can be integrated from 0 to L actually. Okay, so if you integrate this, now let us substitute these values. First of all, what is the expression for this root Rex? Root Rex means Reynolds number at this location is equal to U x by kinematic viscosity. Okay, so square root of this complete value. Okay, so if you take square root of that complete value, let us substitute here. Integral x is equal to 0 to x is equal to L. Tau naught. Tau naught is 0.323 mu capital U by x into this guy, square root of U x by this kinematic viscosity. Okay, so if you simplify these expressions, for example, this this x can cancel this square root of x times, so and of course dx is also there, into b into dx is the total value here. Okay, so let us substitute this expression. So if you substitute, 0.323 is constant, this mu u power 3 by 2 by square root of this kinematic viscosity, into then mu you have taken, so b is also constant, so integral 0 to L 1 by root x dx. So this is the value here. Okay, so if you simplify this value, what you will get? 0.323 into this mu is this into u to the power 3 by 2 by square root of this kinematic viscosity into b times integration of this is actually 2 times of square root of x. So this is 2 times of square root of L. This is the expression for the given values. Okay, so this is the expression for the drag. So drag expression we have already calculated. Now if you replace this with this expression, if you root Rel, what is the value of root Rel? Okay, so square root of Rel is how much? Root capital U L by kinematic viscosity. Okay, so let us substitute these two expressions in this equation. You will get the value of k easily. Okay, so let us see what will be the value of k. Let us take a empty slide. Okay, so this implies, let us see what comes out here. So this implies, now let us see here. Okay, 0.323, okay, 2 times of fd. So 2 times of fd is 2 times of 0.323 into, now mu u power 3 by 2, mu u power 3 by 2 into b into 2 root L, b into 2 times of square root of L divided by this complete value divided by square root of nu into, we have one more thing, rho a u square. So rho area of the plate b into this L into u square is what you have. So this is equal to this constant k divided by this Reynolds number. So if you divide this with, we have square root of nu times, what is there here, square root of u into L, square root of u into L. So from this equation, if you cancel some common terms, then definitely you will end up with this what do you say, you will end up with this k value. Let us see what is the k value here simply. Okay, so this L and this L gets cancelled, then b and b gets cancelled here, then this u square, u power 3 by 2 will leave a square root of u here, and the square root of u gets cancelled. Then what else are the terms that are required here? So this implies, okay, this density into square root of this dynamic viscosity. Okay, so let us see, we can simplify some more terms. 2 into 0.323 into one more 2 is here, so 2 times of mu is there, so mu into root L divided by rho times of root kinematic viscosity here. Okay, so this is equal to k into root of kinematic viscosity. So obviously you can see this combination mu by rho is nothing but your kinematic viscosity. So this cancels one time and this cancels one time, so total this kinematic viscosity term goes out. Okay, so total kinematic viscosity term actually goes out. So k is equal to 2 into 0.323 into 2 times of square root of L actually here. Okay, so we need, of course we have one square root of L here, and this L got cancelled right in this areas. Okay, so did they give you what is the length of the plate? Okay, varies between 0 to L, that's it they have given. Okay, this is root IEL, the value of k is dash, but one root L is actually missing here, correct? So if you calculate this integration of this 1 by root x is actually how much? 2 times of root x, correct? So 2 times of basically x power minus 1 by 2, yes, so 2 times of root x, so you have 2 into square root of L here. So 2 times of square root of L, so 2 times of square root of L we have replaced here, then this is this value, then we have all the other terms as it is. Okay, so this is the value of k. Okay, so where they have given you tau dot b into dx, of course, so integration 0 to L, so mu 0.232 mu u x into u x by kinematic viscosity, then this left u root x, and of course b dx is as usual. So out of this we pulled out constants, 0.323 mu u power 3 by 2, kinematic viscosity is out, b is out, 0 to 1 0 to L 1 by root x dx. So this combination is as it is, integration of this is 2 times of root L, and here half CD times rho a u square, so CD is equal to 2 times of FD by rho a u square. This is equal to coefficient of drag is also given by k by root IEL. Okay, so this is k by root IEL. So these two expressions are same. So if you equate them, we'll get what we'll get here. So 2 times of this FD value 0.323 mu u power 3 by 2 into b into 2 root L divided by square root of nu divided by rho a u square. So rho a u square is equal to k times of k divided by this value. So we have this root into, oh, I think this L is for whole value, correct? So if you see, this square root is for the complete L. Okay, so if this is for the complete L, then obviously it will cancel this L, so no more root L here. Okay, because if you see, that's why this square root is for the complete L. Okay, so if this square root is for complete L, then what happens here? If this square root is for complete L, then this is only root L, then this can cancel is only root times, and this root L will also get cancelled here because of this L. Okay, so this is the expression. So 4 into 0.323 is the value. So if you see 4 into, just a minute, let us see this value, 4 into 0.323. So if you simplify, 1.292 is the K value here. Okay, so this is 1.292. So basically we have equated that, but because of missing this square root here, we actually missed this L. So that's why if you see, we got with this root L gets cancelled, and 1.292 is the coefficient of drag that we have. So 1.292 is within this range that is given. Okay, so that's why when you are writing this square roots and all, you need to be little careful here. Okay, just from the basics, after small calculation, then you can get the value of K directly here. Okay, so let's go for the next question. If the velocity distribution in a laminar boundary layer over a flat plate is given by small u by u infinity, free stream velocity is equal to sine pi by 2 times y by delta. The free stream velocity is 0.5 meters per second and density of air is 1.1 kg per meter cube. Kinematic viscosity is 0.2 times 10 to the power minus 6 meters square per second. Then the mass flow rate that enters the boundary layer at a distance of 20 centimeters is dash in kgs per second. Assume Blasius solution for identifying delta. So let us see. If you have a plate like this, then the boundary layer at this section is something like this. Okay, so this is the boundary layer, for example, and let us suppose this height is delta, this thickness is delta, and you have certain velocity profile. Okay, so let us suppose there is some velocity profile like this, which is given by, you have this velocity profile. So let us suppose u by u infinity is equal to sine pi y by 2 delta. Okay, so sine pi y by 2 delta. Now they are asking you what is the mass flow rate to the exit, right? So m dot. So they are asking you then the mass flow rate that enters the boundary layer at a distance of 20 centimeters is. So basically, let us suppose if this is leading edge, then this is 20 centimeters. So 0.2 meters, for example. Okay, so let us see what happens. So m dot is equal to, if this is a uniform velocity profile, I mean there is a variation. So integral 0 to delta density of the fluid area that is available. So dy into 1 into velocity. So u at that location is u infinity times sine pi by 2 delta times of y actually. Okay, so this is the total mass flow rate. So if you see, rho is constant, u infinity is constant, integration of sine is minus integration of sine is minus cos pi by 2 delta times of y within the limits divided by pi by 2 delta. Again, this is constant value, so within the limits 0 to delta. So if you take 0 to delta minus rho u infinity into 2 delta by pi times of this. If you substitute delta, then we'll have, if you put delta here, cos pi by 2 0 minus, if you put 0 here, cos 0 1. So this minus 1 and this minus gets cancelled. So the total mass flow rate is 2 times rho u infinity delta by pi. Okay, so this is what you have, rho u times rho u infinity delta by pi. Density is given, free stream velocity is given, delta is what you need to identify. Okay, for identifying delta, they have given you assume Blasius solution. So 5x by root rex. So let us see, dynamic viscosity values are given, or at least kinematic viscosity. Kinematic viscosity is given directly. Okay, so it's simple, we can calculate 5 into 20 centimeters means 0.2 divided by square root of u infinity into x. So what is the value of u infinity? The free stream velocity is how much? 0.5 meters per second. So u infinity into x by nu, this kinematic viscosity value. So what is kinematic viscosity? 0.2 into 10 to the power minus 6. So 0.2 into 10 to the power minus 6. Okay, so let us simplify the values, we can get the answer first of all. Okay, so 0.5 into 10 to the power 6. So 0.5 into 10 to the power 6. This can be written as, okay, let's see what comes out. Okay, so 0.5 into 10 to the power 6. 0.5 into 10 to the power 6. So this is the value, and you need to take a square root of that. So take a square root of this. So 1 by x of this into 1. 5 into 0.2 is 1. So basically this value is 1. That's it. Okay, so 0.0014142 meters. So 0.0014142. Okay, so 14142 meters. So these many meters is the boundary layer thickness at a distance of 20 centimeters. Okay, so 5x by root rex. U infinity is 0.5, so it's a very small velocity, and x is 0.2 divided by this kinematic viscosity value. Again they have given us 0.2 into 10 to the power minus 6. So if you simplify this, we got this value basically. Okay, so now let us see what is the value actually. We have taken the square root. 5 into 10 power 5, for example, if you take 5 into 10 power 5, so square root of this and inverse of this. Okay, great. So that's the value. So we got all the values. 2 into density of the flow. How much is the density of the air? 1.1. So 1.1 into u infinity 0.5 is what they have given you. So 0.5 is the free stream velocity multiplied with delta. This guy 0.00141442 divided by this total value divided with pi. Okay, so this is the answer in kgs per second, because if you see, we are calculating the mass flow rate, so the mass flow is in kgs per second. Okay, so let us simplify and substitute here, we'll get the answer. Okay, so 2 and 0.5 can cancel, so that is 1. So 1.1 into this value divided by pi. So 1.1 into this divided by pi. So if you simplify, 0.000495 0.000495 kgs per second is the total mass flow rate that is flowing through the boundary layer that is given here. Okay, so let us check this option. 0.000495, option A is the correct answer. Okay, so we got directly 0.000495. It's very simple. We are applying basic principles of mass conservation or calculation of mass flow rate, all these principles. Okay, so let's go for the next question. Okay, so I think in YouTube live class we have done some analysis on this, but okay, let us see here. Okay, so let us see. Air flows along a flat plate with uniform velocity at inlet. If the plate length is increased by a factor of 2 and if the free stream velocity is increased by a factor of 2. So what they are increasing? Length is increased by a factor of 2, correct? And the free stream velocity is increased by a factor of 2. So u infinity in second case is 2 times of u infinity, for example. Okay, then the drag force will increase by a factor of dash. So if you want to calculate drag force, half into CD. Normally in these plates we can take CD is equal to 1.328 by root REL actually. Okay, so 1.328 by root REL into rho A length into this width, for example, into u infinity square, for example. Okay, so now let us see what is this Reynolds number. Half into this 1.328, or in generally some constant, doesn't matter, as soon as they give this you can write V into or u infinity into L by nu. This is kinematic viscosity into rho times of L into W into u infinity square. Okay, so this is what you have. Now if you simplify this, we'll get this L, cancel this L, root L times, and of course this u infinity can give you this u infinity power 3 by 2. Okay, so rest of the things are constants. Kinematic viscosity is constant, density is constant, width of the plate is constant, nothing is being changed. So one thing is very clear, your FD is actually proportional to u power 3 by 2 into L power 1 by 2. Okay, so this is the proportionality basically. Okay, so now in both the cases, if you take the ratio FD1 by FD2 is equal to FD1 by FD2 is equal to u infinity power 3 by 2 into L power 1 by 2 divided by, in the second case, u infinity 2, which is 2 times of u infinity whole to the power 3 by 2 times of, this is also multiplied, so 2L power 1 by 2. So now if you see this u infinity power 3 by 2 and this u infinity power 3 by 2, similarly these values will cancel out, and 1 by 2 power 3 by 2 is 2 root 2 into square root of 2. So total it is 4. So which means if you see FD2, the drag force acting on the plate in the second case is 4 times of the drag force acting on the first case. So that's why the drag force gets multiplied by a factor of actually 4 in this case. Okay, so the drag force will increase because if you see, it is actually 4 times of this FD1. Okay, so the drag force will increase by a factor of actually 4 times of this existing value. Okay, so let us go for the next question. At the point of flow separation for viscous flow past a solid object, choose the correct statement. So let us suppose if there is some solid object like this. If you have some solid object like this, choose the correct statements. At the flow separation point, so at the flow separations like this, means the flow is getting separated like this, then in such cases, whenever, first tell me one thing, whenever the flow got separated, then definitely there is no contact between the solid and the liquid, correct? Because the flow has already got separated. So when flow got separated, there is no contact between the solid and the fluid. So whenever there is no contact between the solid and the fluid, obviously there is no wall shear stress because the fluid and solid are not in contact. So tau W is basically 0 in this case. Okay, and what are the reasons for this flow separation? One of the very good reasons is adverse pressure gradient. Means the flow, means if flow is taking place in this direction, if this dp by dx is generally greater than 0, then definitely the flow reversal tries to take place and there is a net flow separation at the solid interface. Okay, so dp by dx has to be positive and shear stress at the wall should be 0 because the contact gets avoided. Okay, so let us check what are the options. Axial pressure gradient is non-zero. Correct statements. Okay, sometimes you need to see carefully, they give incorrect statements here. Okay, so axial pressure gradient is non-zero. Yes, this is true because this value is some positive value whenever the flow separation occurs in general. Okay, and wall shear stress is 0. Of course you can see, because once the flow gets separated, then definitely there is no contact between solid and fluid. Fluid pressure reduces to its vapor pressure. False, because if you see, as this flow increases, as this x direction increases, pressure value actually increases than the existing value. It don't fall to the vapor pressure. So this statement is actually wrong because it's a positive pressure gradient. As your flow direction is increasing, means as the x coordinate is increasing, definitely the pressure values also will increase. Okay, so when pressure values are increasing, the actual pressure, means at this location the fluid has some pressure, but here the pressure will be more than this, but it's not below the this vapor pressure. Okay, the magnitude of wall shear stress reaches to its maximum. False, because if you see, the wall shear stress is 0 clearly. Okay, so tau w is 0. So only these two statements are the correct answers. Capital A and capital B are the correct answers in this case. Okay, so let us solve this question. A fluid is flowing over a smooth flat plate with sharp leading edge. The phase time velocity of the fluid is u infinity. The fluid follows the velocity profile, which is cubic profile, at the exit, where y is the vertical distance from the plane. The percentage of mass flow rate lost through the section QS. Where is QS? Okay, here is the QS. Okay, so fine. Here the velocity profile is uniform. It is coming out with some uniform velocity u infinity, for example. Okay, and here you got some velocity profile which is cubic profile. Okay, so there is some cubic velocity profile at the exit, and this is QS. So what is the discharge to this Q, basically to this section QS? They have asked this, and we have done this question many times even in differential analysis when we go for the mass conservation. Okay, so Q is nothing but the mass flow rate to PQ minus the mass flow rate to RS. Okay, so the mass flow rate to the RS values. Okay, so now if you see, this implies Q is equal to integral 0 to delta. Here the velocity is uniform, so u infinity into b dy. Let us suppose if width of the plate is b, then u infinity into b dy. Width of the plate is given. Okay, nothing is given. They are just asking you what percentage of mass actually flows. Okay, so if they want percentage, then definitely you can divide this with, let us see, if you want percentage, then definitely the actual mass that is coming is m dot p. So q by m dot pq into 100 is what you actually want. Okay, so this is equal to 1 minus mass flow rate of RS divided by mass flow rate of PQ. Okay, so let us see, 1 minus, what is the mass flow rate to RS? At RS you have this velocity profile, integral 0 to delta. So what is the velocity profile? 3 by 2 times of y by delta, 3 by 2 times of y by delta minus half times of y by delta whole cube, half times of y by delta whole cube dy. Okay, of course b is also there, for example b dy, plate width is not known to you, so b into dy. So divided with mass flow rate that is actually flowing through QPQ, 0 to delta. At P to Q the velocity has a uniform velocity profile, so u into there is also u infinity here. Okay, u is equal to u infinity into this value, so we have this multiplied with u infinity into b dy. Okay, so this is the integration you need to carry out. Similarly here, u infinity into b into dy. So now it's very simple. If you see, this u infinity into b are constants in this integration. So let us integrate. What comes out? Let us see. 1 minus 3 by 2 times of 3 by 2 delta times of integration of y is y square by 2 minus 1 by 2 delta cube into integration of y cube is y power 4 by 4 within the limits 0 to delta, and here the denominator value is delta actually, correct? Because if you say integration 0 to delta, this is dy, so this is the value. So 1 minus, let us simplify this. If you simplify this, we have 3 by 4 times of delta, 3 by 4 times of delta minus delta by 8 by delta. So this delta cancels out, so 1 minus 3 by 4 minus 1 by 8, which is 6 by 8 minus 1, so this is 5 by 8. So total 3 by 8 is the value. Okay, so this much fraction of mass is actually passing through that section QS basically. Okay, so this QS, so mass fraction that is passing through this QS is 3 by 8, but since they are asking in percentage of mass flow is equal to percentage of mass flow is equal to, how much is this mass flow value? So this Q by m dot pq into 100%. So this value is actually equal to 3 by 8. So what is the value of 3 by 8? 3 by 8, 0.375. So into 100, so 37.5% of the mass is actually flowing to the 37.5% of the mass is actually flowing to the section QS. Okay, so 37.5 is within this range. Okay, so 37.2 to 37.8. So 37.5% is the mass flow that is flowing to this QS. So let us see this question. An NSG commando of mass 60 kg descends to the ground from an airplane with the help of a parachute of mass 20 kg against the resistance of air. The shape of the parachute with which it comes down is hemispherical. Okay, so there is some hemispherical with 2 meters in diameter. If CD is 1.5 and density of air is 1.25 kg per meter cube, then the velocity of the man is dash. So see here carefully, there is a hemispherical parachute like this. Okay, so let me make it hemispherical first. So let me make it some hemispherical parachute first of all. So let us make it some hemispherical parachute first of all. Okay. So to this hemispherical parachute, we have suspended a person. We have suspended a person like this. Okay. So let us suppose there is a person to this. Okay, so there is a person who is coming out with this parachute. Okay, now let us see. Obviously this person's velocity is controlled by the drag force acting on this hemisphere, correct? So if you see, the weight of man plus weight of parachute, these two acts bottom in the downward direction, and of course if you see, there is some drag force of the air that acts on the parachute in the upward direction, so that there comes some equilibrium between this and the person comes out with some steady state velocity. Okay, so let us see what is the equations here. So if you see, this FD should be balanced by this weight of the parachute plus weight of the man actually. Okay, so what is the FD value? Half CD density of air, because the medium is air, area of the surface area. Okay, so area of projection, if you see, this is a hemispherical value, so A into U infinity square. So this is equal to weight of the man plus weight of the parachute, which is mass of the man plus mass of the parachute into gravity. Okay, so let us see now what they're asking you, this U infinity, because if you see, if man is coming down with a velocity U, then the parachute also comes down with a velocity U. Okay, now if you see, air is traveling in this direction, so if air is traveling in this direction, then the surface area which is projected onto the perpendicular is half of the it's basically a circle, correct? So it is a circle, so pi d square by 4 is the projected area. This is AP, so AP is equal to pi d square by 4 because the air is flowing. Okay, so if you see, the drag force is in this direction, the vertical force. So if air is flowing in this direction, then definitely this total means the projected area of this hemisphere perpendicular to this flow direction is a circle in the top view. Okay, so let us see these values. Half into CD, so drag coefficient they have given you directly, they have given you 1.5. so let us write 3 by 2. Density of air 1.25, so 1.25, let us write 5 by 4 for example. Projected area pi d square by 4, pi d square, what is the diameter? Diameter of the parachute is 2 meters in diameter, so pi d square by 4 into U infinity square, that is not known to you, is equal to mass of the man. He is a 60 kg commando and parachute is 20 kg, so total 80 kg into gravity. Something is given about gravity. Okay, nothing, so let us take 9.81. So from this value you need to calculate some expression for U infinity. Okay, so let us see what we can do. 4 and 4 gets cancelled, so that's it. So 5 can cancel this 16 times. Okay, 5 can cancel this 16 times, so I think these are the calculations. So U infinity square is equal to 4 into 4, 16 into 16, so 256 times of 9.81 divided by 3 times of pi. Okay, so we need to calculate this U infinity value. Let us calculate this. 256 into 9.81, 256 into 9.81 divided by 3 times of pi, 3 times of pi. Okay, so divided by 3 times of pi, and you need to take a square root of this. So if you take a square root of this, 16.3237 meters per second is the velocity at which the person will actually come down. Okay, so this 16.3237 is the velocity. So 16 meters per second, it is reasonably a very comfortable velocity to land. So 16.3237 meters per second is the actual velocity with which the person comes out. Okay, so 16.23 something 16.32. Okay, so 16.3237 is the velocity in meters per second. So 16.3 is in between 16.1 to 16.5. Clear? So that's how we can solve this question. So let's go for the next question. For the motion of a boat in a stream, the coefficient of drag is found to be 0.3. Okay, if after polishing the hull of the boat, the coefficient of drag decreases to 0.25 and the same diving power is utilized, then the percentage increase in the speed. Look, if you see, there's a boat, there's a solid, so F drag acting on this is half CD rho a u infinity square, for example. Okay, so we know if you want to reduce the drag, you generally streamline the bodies, or you generally polish them actually to make them smooth. Okay, so half CD times of rho a u infinity square is the value. So let us see, this CD value is given. So area of the hull is just polished. Okay, density remains same and everything. So let us see what comes out. Okay, this is the drag force, but diving power, so power is utilized in drag is actually equal to half CD rho a u infinity square into the motion of the boat is 1 more u infinity, so total u infinity cube. Okay, because power is equal to force into velocity, so one velocity if you multiply, this is the case. Okay, now out of these quantities, the half is a constant, density of the water is constant, and area of the boat is also constant. It is just polished. Okay, so this implies power is actually proportional to CD times u infinity cube. Okay, so that means if you take two cases, power in first case by power in second case is equal to CD in the first case divided by u infinity cube in first divided by u infinity, let's take for example u infinity whole cube, and in the second case CD in the second case into u infinity 2 cube. Okay, now it is given to you that the power utilized in diving is same in both the cases. Okay, so this means CD1 or CD2 by C, if you want, what they're asking you finally, the percentage increase in the speed. So means they're asking you u infinity 2 minus u infinity 1 by u infinity 1 into 100. So this is the percentage increase in the speed. So they want this value. If they want this value, you need u infinity 2 in terms of u infinity 1. Okay, let us do that. U infinity 2 whole cube is equal to u infinity 1 whole cube into CD1 by CD2. Okay, so this implies u infinity 2 is equal to u infinity 1 times of CD cube root of CD1 by CD2. So what is this value of CD1 by CD2? In first case 0.3 and in second case 0.25. So 0.3 by 0.25. Okay, so this is the elation. So this is the elation. If you substitute here u infinity 1 into cube root of this, so finally you will get cube root of 0.3 by 0.25 minus 1 into 100 into 100. Okay, so this is the value that you will get here. Okay, so 0.3 divided by 0.25. Let us simplify this value and see what comes out. 0.3 divided by 0.25. Okay, so cube root of this, so cube root of this minus 1, so into 100 into 100, so 6.2658. 6.2658% is the increase in the velocity of the boat actually. Okay, so 6.2658 is the increase. Okay, so 6.28 is again within this range, so 6 point round off to 2 decimal places. So what is the third decimal? 5. So this is even number, so 6.26% is the percentage increase in the velocity of the boat for the same diving power that is supplied to the boat. Okay, now let us go for the next question. A ball has a diameter of 40 mm and falls in honey with a terminal velocity of 0.3 meters per second. Assume it is a steady flow and honey is incompressible. The mass of the ball is dash grams. Okay, so let us see what is the weight of the ball actually. So now if you see the motion of the ball, there is a ball like this. The weight of the ball will be acting downwards. So weight of the ball acts downwards here like this. So W of the ball. Now on this ball there is viscous force. F viscous. And since the ball is moving at steady state, then definitely the net force acting on the ball is 0. These are the two forces, and of course buoyancy is also there. So let us see, did they give you density of honey? Yes, density of honey is also there. Okay, so frankly speaking, there is viscous force, along with that there is also buoyancy force. Okay, but okay, so 40 mm diameter, so let us take, because the ball is actually traveling, so there is some buoyancy force also. Fb, buoyancy force, that is acting. Okay, so let us see, write the equilibrium. Weight of the ball is equal to viscous force plus this buoyancy force. So mass of the ball into gravity is equal to viscous force. So what is viscous force? You know, viscous force is nothing but the drag force here because of the fluid. So half CD. So what is CD value? Did they give you? They haven't given you the CD value, right? So CD is nothing but, for spherical bodies, this is 24 by Reynolds number. So 24 by rho Vd by mu, rho Vd by mu actually here. Okay, so I think these values might be given to you. So 24 mu rho Vd. Okay, so CD is that value. So 24 mu by rho honey into velocity at which it is traveling into d, half CD into rho A. What is the projected area? So if you see, this is a spherical shape, so sphere has a projected area of circle whenever there is some projected area. Okay, so this is pi d square by 4 into half CD rho A u square, so v square again, plus buoyancy, density of the honey into buoyancy is nothing but pi d cube by 6 times this is g. So this is the total expression. Okay, so now let us simplify the common terms. So density of honey and density of honey gets cancelled. This diameter can be cancelled one time here, and this velocity can be cancelled one time here. Then 2 4s are 8, so this is 3 here. Okay, so this is 3, and here there is, I think, nothing much to simplify. So mass of the ball into gravity is equal to, how much is this value? 3 mu pi dv plus density of honey times of pi d cube by 6 times of gravity. So you can do one thing, since your interest is this mass of the ball, let us cancel this. Okay, so mass of the ball is equal to, let us see how many kgs, 3 into pi into g 9.81 into mu dv. So what is the dynamic viscosity of honey? Okay, kinematic viscosity they have given you directly. Okay, so kinematic viscosity, but you need dynamic viscosity. So dynamic viscosity is nothing but product of these two, density into this kinematic viscosity. So 1360 into 0.04, 1360 into 0.04 into diameter of the ball. They have given you, yes, 40 mm diameter. So 40 into 10 to the power minus 6 into velocity. At what terminal velocity they want this? They want it to be 0.3 meters per second. So 0.3. So 3 into 10 to the power minus 1 plus 1360 density of honey into pi into 40 into 10 to the power minus 3 whole cube. So 4 cube is 64 into 10 to the power minus 6 is what you have. Okay, 4 into 10 to the power minus 2 meters. So that is pi d cube by 6. So this is the total value which you need to calculate for getting the mass of the ball. So let us do this quickly. So let us see what we can eliminate here. Okay, so I think nothing much can be eliminated, but let us do one thing. Okay, so let us simplify. Let us start simplifying from this term. So 1360 into 0.04, 1360 into 0.04, 1360 into 0.04 into 40 into 3, so into 120 into 120 by 10 power 7 totally. So divided by 10 to the power 7. So divided by 10 to the power 7. So you got this value into 3 pi by 9.81 into 3 into pi by 9.81. So if you simplify, this is what we have, 0.000627, 0.000627 plus, let us see this value. Okay, so 1360 into pi into 64, 1360 into pi into 64 by 6 this value divided by some 10 power 6. Okay, so divided by 10 to the power 6. So 0.0455, 0.0455 actually. Okay, so if you sum up these two quantities, let us see how much you get, plus 0.000627 0.0627 something. Okay, so 0.04620, 0.04620 is the value here. Okay, so this is the mass of the ball in kgs. So in grams, if you want, this is 446.2 grams is the ball, is the total mass of the ball actually. Okay, so 46.2 grams. Okay, 671 is given, 673. How come? Density of honey, everything we have substituted correctly, right? So let us see this expression, 24 by Reynolds number. So 24 by Reynolds number is nothing but rho VD by mu. So this mu goes onto the top. So 24 mu by rho VD, 24 mu by rho VD into half CD rho A. A is pi d square by 4 because it's a circle in projection. So if the fluid is traveling, then the sphere has a projection of a circle. So pi d square by 4 into V square plus buoyancy force acting is density of honey into pi d cube by 6 is the volume. Pi d cube by 6, right? 4/3 pi r cube. So if you convert this, 4/3 pi d cube by 8. Okay, so yes, pi d cube by 6 into g. So g gets cancelled, and here we made some simplifications. 2 4s are 8, 8 cancels 24 times. Then OH V D cancels, OH D V one time. So 3 is left here, mu pi d v. That's it, no more denominator, plus OH into pi d cube by 6 into g. G gets cancelled, and we have a g multiplication here. So 3 pi by 9.81 is constant. This mu can be written as kinematic viscosity 0.04 meter square per second into 1360 So this is mu value, this is diameter 40 into this is d, right? So d value is how much? D value is 40 mm. Okay, so 40 into 10 to the power minus 3. That's why we have made minus 6 here. So this is 10 to the power minus 3 into velocity is 0.3. Velocity is 0.3 means 3 into 10 to the power minus 1. Of course, then this calculation first term will go wrong. So let us see what is the first term value. Okay, so let us see what is the first term value in that case. But second term is density of honey pi, this 40 into 10 power minus 4 into 10 to the power minus 2. So cube of that, 4 cube is 64, 10 power minus 6 divided by 6. Okay, so I think that's fine. So let us calculate this value once again. Okay, so let us take that value also first. 1360 into pi into 64 divided by 6 divided by 10 power 6 10 to the power. So 0.04557, 0.0455. Okay, 7. Now let us see what is this value once again quickly. So 10 to the power minus 3. Okay, so let us see what happens out. 1360 into 0.04, 1360 into 0.04 into 40 into 3, 120. So 40 into 3, so 120. So this value divided with 10 to the power 4, divided with 10 to the power 4 actually. Okay, so 10 to the power 4 into 3 pi by 9.81 into 3 into pi by 9.81. So this is the value 0.62716, 0.62716 grams. Okay, so this, if you add both these things, so let us see how many grams is this. This value plus 0.04557. Okay, so 7. So if you simplify, 672.73, 672.73 grams. You understood this buoyancy is actually very small because the diameter of the ball will be very small actually. Okay, so 672.73 grams. So let us see, 672.73 is within the range. Okay, so 672.73. The only thing that we have made some change is in this value, this 10 power minus 3 we have replaced as minus 6. So that's why answer got changed. Okay, so 672.73 grams is the correct mass of the ball that can actually flow. Okay, so let us go for the next. Okay, I think questions are finished. So yeah, this is basically our team for the mechanical, PI and XC, of course. Okay, so we have a very good mix of faculties all over here, including all India rank ones, and people who worked at public sectors, people who have done some good research in the teams and all. So we are going to basically take out to the mechanical and PIXC courses for all of you if you get enrolled in the courses. Okay, so and this we have recently launched this test series launch is also came, and of course if you see in the library section of PW app or website, you have this Gatopedia which we have done, which our team has basically put a lot of efforts to bring it to you. Okay, so that's why if you see This Gatopedia is like one of the very good resource for all the students who are going for GATE 2023. Okay, so please do utilize that. You can download it from the library section of PW app. Okay, so we'll meet on Monday again at 11 a.m. for our problems on turbulent flow and dimensional analysis, which is one very important chapter. Again, dimensional analysis is one really good chapter, so try to attend that also. Okay, on coming Monday at 11 a.m. Thank you all. Okay, so we'll meet again at 11 a.m. on Monday. Thank you.